Welcome to the step-by-step tutorial on digital logic design. Today we are utilizing the Quartus 2 software to create a schematic block diagram for a vital signs monitoring system. This circuit is designed to analyze a patient's health data and provide real-time feedback based on critical parameters. We begin our design process by placing the initial input pins onto the workspace. To maintain professional organization, we carefully rename each pin to correspond with a specific medical sensor. Here, we are defining inputs for body temperature, pulse rate, the respirator system, and oxygen saturation levels. Once our inputs are properly labeled, we navigate to the symbol library to select the necessary logical components. For this specific monitoring logic, we are incorporating a series of NOT gates and multi-input AND gates. These components act as the brain of our circuit, forming the logical structure required to process sensor data accurately. We arrange these gates systematically on the grid to ensure the layout is clean and easy to follow. Finally, we introduce the output pins to the diagram. These outputs are responsible for triggering the final results, such as activating an emergency alarm or a status notification. By following these steps, we have successfully mapped out the digital framework, making the design fully prepared for the upcoming stages of wiring and functional simulation. Moving forward from the initial layout of our inputs and logic gates, we now proceed to the connection and verification phase. In this stage, we utilize the orthogonal wiring tool to precisely link each input pin to its corresponding logic gate according to our design specifications. It is crucial to ensure that every connection is solid and correctly routed to avoid logical errors. After completing the wiring, we perform a final review of the schematic before saving the project. Next, we initiate the compilation process. This is a vital step where Quartus 2 analyzes the design, checks for syntax errors, and maps the logic to the hardware. You can monitor the progress through the status bar as the software runs the synthesis and fitting stages. Once the compilation is successfully completed with 0 errors, we are presented with a detailed flow summary. This confirmation indicates that our digital monitoring system is now logically sound and ready for the final simulation and waveform analysis to verify its behavior. Building on the successful completion of the compilation and the generation of the flow summary, we now transition into the simulation phase to rigorously validate the functional behavior of our digital monitoring system. To begin this critical stage, we navigate to the File menu to create a new University Program VWF, which serves as the primary environment for waveform analysis and verification. Once the editor is open, we utilize the Node Finder tool to bridge our schematic design with the simulation interface. By selecting the Pins All filter and clicking the List button, we can identify and import every input and output node directly into our waveform file. It is essential at this point to organize these signals logically, placing our primary sensor inputs at the top to facilitate a clear visual comparison against the resulting output signals. With the nodes properly arranged, we proceed to define the input stimuli by setting the simulation end time and grid size to match our testing requirements. We then manually assign specific logic levels, logic high and logic low, across the timeline to simulate various real-world operational scenarios. This allows us to observe how the system handles different sensor combinations, such as simultaneous triggers or sequential input changes, by toggling the values between 0 and 1. After configuring these input patterns, we initiate the functional simulation. During this process, Quartus 2 calculates the logic state of each gate in our schematic and generates an output waveform that represents the system's real-time response. We must then carefully analyze these resulting waveforms, ensuring that the output transitions precisely align with our design specifications and logical truth tables. By verifying that the system behaves correctly under every tested condition, we provide empirical evidence that our digital monitoring system is logically sound. This final verification marks the successful conclusion of the design cycle, confirming that the project is now fully validated and ready for physical hardware implementation.